let us start. Now, we have learned how to obtain the model describing our calibration method. But we need now to calculate the confidence interval for the interpolated value. That is, I will replot our problem. We have prepared several standards of known concentration in a convenient solvent. We apply the external standard method. So we obtain several measurements, and by regression we calculate the model that is the best estimation of the calibration function. And now we need to associate the concentration interpolated to an unknown sample, the concentration interpolated by starting from the area obtained from the unknown sample that I have symbolized by A0, and interpolating it on the model, we obtained C0. The model has equation area equal to intercept plus slope multiplied concentration. So you see that it is very easy to calculate C0 from A0, because if this equation holds true, it is also true that the area relevant to the unknown sample is equal to intercept plus slope multiplied with the interpolated concentration. And so the interpolated concentration for the unknown sample is the area of the unknown sample minus the intercept divided by the slope. So it's very simple to calculate C0. What is less simple is to associate to C0 the absolute error, that is calculating the confidence interval for the interpolated concentration. And in order to describe how to obtain this confidence interval, we can discuss in a similar way as we did for the intercept and the slope. So imagine that you can repeat the same experience in the same conditions infinite times, and then you can plot all the possible obtained values for C0 and plot the probability as a function of those values. You will have a Gaussian distribution where the maximum, the point of maximum, will be area of the unknown minus intercept divided by B, the slope. And this distribution will have standard deviation. Let us symbolize it by S0. We have a formula that calculates S0 as a function of all the quantities involved in the problem. This is the result of a demonstration. There is an article, a very old article demonstrating this formula, and I'm going to write down it. I will never ask you to learn it by memory, but simply look at it to discuss. S0 is equal to ratio between standard deviation of regression, that is the quantity that was minimized in order to calculate intercept and slope, divided by the slope and multiplied by square root of 1 over n. N is the number of measurements on the standard sample. That is the number of times that we have measured the area for a standard. Okay, the number of times we have measured an area for a standard. Then we have 1 over m. M is the number of replicates, number of measurements on the unknown sample. We imagine that if we have injected in the LC our unknown sample m times. So one injection, another one, m times. And we take the average of the area obtained with the unknown. Okay? Let us explain using this. Here I have plotted one value of A0, imagining that I have performed only one injection of the known sample. I can perform the injection n times and take as A0 the average. So I inject my unknown, I obtain an area, then I inject another time, and I make the average of all the obtained area from the unknown sample. I have replicated the injection of the unknown m times. Is that okay?
Is that n?
N in this plot is 5 because I have measured area for the standard 1, for the standard 2, 3, 4, 5. But in general, we prepare 5 classes of standard samples, and each of them is processed many times. So suppose, for instance, that you have 5 standards, but each of them is injected 3 times.
Exactly.
Means that you have performed 15 measurements.
Okay.
Okay, so n is 15. And in general, it is done like that. In general, we inject a standard sample many times. 3 is the most used choice, but also 4, 5. It depends on the time and chemicals that you have available.
Okay, but n, instead n is a mean.
M is the number of times that I have injected the unknown.
Yes.
And I will consider the average of the area obtained for the unknown. So this A0 will be the average of the areas obtained when injecting n times the unknown.
Okay.
Then we have ratio. Here we have, in the numerator, we have A0, the average, because we have injected the unknown sample n times, minus A average and I will explain what it is. Square. What is A average? Average area. It is the sum of the areas obtained for the standards divided by the number of measurements performed on standard samples. So, in this case, we have only 5 values of areas, area 1, 2, 3, 4, 5. We sum all of them and divide by 5, and we obtain the average value of the areas for the standard samples.
But N is the number of standard.
N is the number of measurements performed on standard samples. So, in the example we did before, if you have 5 standards, but each of them is measured 3 times, you have 15 values of area. And in that case, A average will be the average of those 15 values of areas. Okay? And this value is a point of the straight line exactly in the average, in the middle. Okay? So this point, green, the green point has the ordinate equal to A average.
Allora, A average is the sum of the area for standard.
Yes.
So it should have a value that is on the ordinate.
Yeah.
Divided, okay, for the number of
The average, it is exactly in the middle between the lowest and the highest value of areas for the standard.
Okay, so for me, in this plot, this average is on the ordinate, not on the
Yes, the average is here, but there is a point of the straight line having that average as ordinate.
Okay.
So this green point has as ordinate the average of the areas that we have read for the standards. Of course, this point has an abscissa, and it will be the average of the concentrations of the standards. This special point is important. It is called centroid. Now we go on and complete the formula. In the denominator, you have again the slope, but it is squared. And it multiplies the sum for I going from 1 to n of these quantities, Ci, the generic concentration of the standards, minus C average, the concentration in the middle, square. So the C average is the sum of the concentrations of the standards divided by n. Okay, this is the formula. Now let us discuss it. Do you agree that our purpose is to have a very low value for S0 we want S0 to be small. We want high precision on S0. Okay? So let us consider the influence on S0 of all the parameters. How should Sy over X be? Small. How can you obtain Sy over X small? Making an accurate work. So trying to be very careful in preparing standards and injecting in order to have the points not so distant from the model. B is sensitivity. So we should choose a method where sensitivity is high. N should be high or low, big or small. N should be a high number, as high as possible. It depends on how much time I have and how much of consumables, of chemicals. So I perform as many measurements on standards as possible. And the same holds true for N. Do you agree? Okay. And what about this difference? The area obtained for the known minus the area in the middle of the curve. It should be small, possibly exactly equal, possibly. It means that the best case is when this signal, this area of the unknown is close to the middle. Okay. It is hopeful to have the area of the unknown very close to the average of the areas of the standards. Okay?
No, because if I take, for example, if the unknown sample has a very small concentration, I don't expect that it will be closer to the middle of the...
Yes, your sentence is correct, but look, we haven't yet decided the concentrations of the standards. So the correct way of discussing it is this. I have to choose the values of the concentration of the standards in such a way that their average is close to C0. Or the average area of the standard is close to the area of the unknown. In fact, at the end of the discussion of this formula, I will tell you how do I proceed practically. Okay? How can I decide the concentration of the standard? Okay, I will repeat now. I want the area of the unknown to be close to the average of the areas of the standards. Do you agree that this is equivalent to say that I want C0 close to C average? It is equivalent, okay? Having A0 close to A average is equivalent to have C average close to C0.
Sorry, Professor, but A0 is still an average.
Yes, it is an average of all the readings of area of the unknown. You have an average here.
But in the formula we have CI, not C0.
We have CI in the denominator, but in the numerator, you have that A0 should be close to A
Yes,
average. This implies that C0 is close to C average. It is equivalent.
No, sorry, I totally lost
Yeah.
the point. Like,
Okay.
I probably lost the slide with centroid, and now I don't know what it like. The letters, what do they represent?
Which letters?
Like A0 average.
A0 average in this plot is the average value of the area for the unknown sample. So I have taken the unknown sample, I have measured it n times, I take the average of these areas of the unknown. A0 is this.
So I made lots of measurements of this unknown, right?
M is the symbol that in general we perform the injection of the unknown 3 times. So we read the 3 numbers and we make the average. And this is the area of the unknown sample, the average.
And what is the centroid?
What is?
The centroid.
The centroid is here, where you have an area equal to A average. And here you have a concentration equal to C average.
Okay, so we said that we want A0 average and A average as close as possible.
Yes.
And it implies that C0 average is close to C average.
Yes.
Okay, so it is always there, but saying A0 average and A0 is the same, right? Because
Equivalent.
it is equivalent. Because probably I am a little confused on. Well, we said that A0 is the number of replicates on the unknown.
Yeah.
So the number of
A0 is the average area obtained for the unknown when we injected the unknown m times.
And so if we inject it just one time, we have just
Yeah.
the A0.
Yes, you can do that,
Oh,
and
okay.
m is equal to 1.
Okay,
Okay.
fantastic.
Then we complete the discussion observing this sum at the denominator. Should this sum be big or small? Big. You want a big sum. What are the elements of this sum? They are C1 minus C average squared plus C2 minus C average squared and so on. So this sum is high, it is big, when the first standard C1 is far from C0 or C average. We want that the concentration of the most diluted standard is very, very low with respect to the average of the concentrations of the standard samples. And the same holds true for the highest, the most concentrated standard. I can just call it Cn, but n can be confusing because it is the number of measurements. Let us call it Cn uppercase. Okay? Oh, more simple, C5 in this example. Okay? So in this example, C1 is the concentration of the most diluted standard, and C5 is the concentration of the most concentrated standard. Okay? So, in order to make that sum big, we want that C1 is as low as possible and C5 is as high as possible. Did I explain in a comprehensible way? Did I? Want me to repeat? Okay, I will try to go on with an example. Okay? I think it is good now to make an example of an experimental procedure. Okay?
So, Professor, this is the formula we don't have to remember by heart?
No, you don't have to remember. In case at the exam, I will write the formula and ask you to discuss. Okay, let us do a simple example. Suppose that we have a sample, so unknown, the unknown. We inject the sample in the LC system once, because we have few time, once, and we obtain an area, I invent the number, okay, 50. The computer tells to me, okay, the area of the peak of your unknown is 50. Usually it is expressed as arbitrary units. And now I would like to know, but if the area of the unknown is 50, can I estimate the order of magnitude of C0? Order of I will write the text. Can I estimate the order of magnitude? Of C0? I would need K, because I know that A0 is proportional to C0 by the constant K. Okay? Are you following me? Of course, I don't know K, because I am estimating it. But by consulting the scientific literature, I can have an idea of the order of magnitude of K. For instance, we find that in the literature, we find a scientist who has performed a similar measurement and K, order of magnitude of 10. So I can estimate the order of magnitude of C0. How much is it? Five. Suppose that the unit is molarity. Did you study molarity? Okay. 5 molar. Too much 5 molar. Millimolar. Okay. I know that the centroid of my model should be 5 millimolar. So I will choose C1, C2, Cn so that the average will be 5. Okay? So for instance, 1, 3, 5, 7, 10, the average is around 5. Okay? Is it clear for you? So, if the order of magnitude of C0 is 5, means that I have, where can I write it? Here. I have to choose, I should choose C1 up to C5 so that C average is around 5. Okay, this is the criterion. Once I have this value, I simply have to choose C1 up to C5 as far as possible from 5. So, the discussion on the sum suggests to me that C1 is far from C average.
Yes, of course.
So I want C1 to be as low as possible with respect to C average equal to 5. So, for instance, if we have where can I write it? Here. So the first choice,
Professor, can you tell me if it is right? Once I have the centroid that is equal to 5, I want to choose a C1 that is as far as possible from 5.
Yes, that is as low as possible.
Okay.
So this is the first requirement. The second is that C1 should be as low as possible. And of course, C5 should be as high as possible. For instance, I will write a series of numbers for the concentrations that is wrong. So I prepare a standard whose concentration is 5. Exactly, I can do it. And then I choose 4.9, 4.8, 5.1, 5.2. And the other choice, so these are the 5 choices for C1, C5, C1, C5, okay? And another one could be 1, 5, and then I put here 3, and then 7, 10. So I enlarge the range of concentrations of the standards. The second is better because I have enlarged the range of values for the concentrations of the standard. There is a limit in lowering the concentration because if we lower the concentration, if the concentration becomes very small, the area becomes very small, and at a certain point it is confused with the noise. So it is no more readable. I mean, the instrument has a minimum value of area that can be detected. It is called limit of detection. The minimum area readable on the instrument is called the limit of detection for the area. Okay. And when I increase the concentration, there is a problem of linearity, because if the area is too high, we lose linearity. And we must work in such a way that the area is not too high. When you obtain a liquid chromatogram, the number on the ordinate can be an absorbance, for instance. Let us make the example that S is an absorbance.
So the A is an absorbance. Essentially, the A is an absorbance.
And the number on the ordinate of the chromatogram can be a number of several quantities. It can be an absorbance. If the detector is a spectrophotometer, you have an absorbance.
So my A is an absorbance.
A is, we have used up to now as the area, so we can get confused. Okay. That's why I write absorbance extensively. Okay. So, for example, the number on the ordinate of the chromatogram can be absorbance. And there is an empirical rule for which, if absorbance exceeds unity, we lose linearity. So we should have the maximum area such that the height is not higher than 1. So I repeat, in the case that the ordinate of a chromatogram is an absorbance, the maximum height of a peak should be below unity. So the area should be such that the height is not higher than unity. This is an example. So in general, I say that in order to choose the concentrations of the standards, at first I estimate the order of magnitude of the centroid for the concentrations. Then I choose the minimum concentration of the standards as low as possible, but higher than the limit of detection. And I choose the concentration of the most concentrated standard as high as possible in the limit of linearity of the signal, of the area. There is a test that can check for linearity, and we will discuss it. Okay? So this is
Professor.
yeah.
So we need to check the linearity and also the limit of
limit of detection. The minimum signal, the minimum value of the ordinate in this plot, the minimum readable value of the ordinate in this plot.
And the limit of detection
is sorry, there was another here.
The limit of detection is
I have written P.
Yes.
P and probability is what was wrong.
Me too. Instead is an area.
Yeah.
Okay. The limit of detection instead is written on the instrument, I imagine.
The limit of detection is evaluable from the instrument, from the method, yes. And I'm going to discuss how to evaluate the limit of detection just now. Okay.
I thought also
Yeah. And the limit in the high concentrations is to stay in the linear range.
Yes.
Okay. So let us discuss what is the limit of detection. Limit of detection. Now it is more simple in explaining this to use a generic formula for the model. So I will write the model as y response equal to intercept plus slope multiplied x. In the example of chromatography, y is an area and x is the concentration. In the example of spectrophotometry, y is an absorbance and x is a concentration. So y, now I will, from this point on, I will call y the signal for the simplicity, for the break, okay? So y is our signal. Is it clear for you? Now, the limit of detection, another thing to be told before giving the definition. The matrix, that is all the chemicals that are together with the analyte, the matrix is also called the blank. Matrix, also called the blank. So the blank is a system where we have all the stations except the analyte. Okay? Okay, the definition, limit of detection. The limit of detection is the minimum signal that is significantly different with respect to the signal of the blank. Okay? In order to quantify the concentration, the minimum concentration corresponding to the limit of detection, we must proceed as I will show to you. So, limit of detection, minimum signal, but the limit of detection is the same term is used for the minimum concentration. So we can also say that the limit of detection is the minimum concentration giving a signal that is significantly different with respect to the signal of the blank. Okay?
No, can I repeat just a second? It corresponds to the limit of concentration, that is the minimum concentration, significantly different.
The limit of detection is the minimum concentration giving a signal that is significantly different with respect to the signal of the blank. Let us try to write some symbols. So, I define YLOD, limit of detection, LOD, minimum signal, significantly different from the signal of the blank, YB, is the symbol that I adopted for the signal of the blank. Okay? And CLOD, minimum concentration, it is the minimum concentration giving a signal Y log significantly different from YB. Okay? And we want C log. How much can we go down with concentration with our method? Which is the minimum concentration that we are able to obtain?
Is C log our C1?
C1?
The first.
It depends. It should be. It should be. Yes. C log should be lower than C1. If this does not happen, you should eliminate C1 and recalculate the model. CLOD should be lower than C1.
Why not the same?
This is another empirical rule. Usually we choose the C1 at least twice C log. I think that I forgot to write the confidence interval for C0 because I have written this. Of course, the confidence interval for the unknown is so confidence interval for the unknown is C0 plus minus T tab multiplied S0. Okay? I haven't written it, but in general, the confidence interval is obtained by taking the central value, that is in this case is A0 minus A divided by B, plus minus the t tabulated of the problem multiplied with the standard deviation of this parameter. So I have forgotten it, sorry. Okay?
Ma it should be C0 should be A0 minus A
Yes.
over B,
Yes.
right?
This is the value of C0 calculated from the problem. And this, on the x-axis, I have all the possible values for C0. The same holds true, C0 plus minus delta C0. So delta C0, the error on C0 is theta multiplied as C0. Okay? Okay, now we go on with the limit of detection. And I will try to explain to you how we calculate CLOD. What's the problem? Please tell me.
It's just, I can understand because sometimes we put the 0 with the bar and other time no, and so.
In which formula?
In the one we have just the confidence interval for C0.
C0 comes from this calculation. That is the area of the unknown minus the intercept divided by the slope. So it is not an average. It is this calculation. It is not an average. It comes from this calculation. Because you see, this is the relationship between A0 and C0. A0 is equal to the intercept plus the slope multiplied C0. So C0 is obtained in this way.
Yes.
It is not an average of direct measurement. It is interpolated. It is an interpolated value.
Yes, I know.
So when would you like to see an average?
No, sorry, probably I didn't explain well. Not the bar over the number, but the bar over the 0.
It's simply a way of expressing it. It is always 0, sorry.
Okay.
And because the bar is to say this is 0, it is not O, it is not a letter, it is a number. So I should
it's the same thing.
Yes, of course, the same. Yes, it is simply a way of indicating to distinguish the number 0 from the letter O because they are very similar.
No, okay, because in the first slide, no, in the previous slide, probably there was when we wrote the error.
Oh, okay.
The confidence interval. No, not this one.
Here I put the bar.
Yes. The one still written, the confidence interval for C0.
Here I put it, okay. When I don't put it, it's because I forgot. But it is 0. I call it 0 and it is 0, okay. Not to make a confusion with respect to O. This is 0 and this is O. Simply a symbolizing. It is not a matter of concept, simply symbols. So C0 is the concentration of my unknown, and it is calculated by interpolation. Okay. So also here it is missing, it is 0, and also here.
No, okay, it's just okay.
We make it. Sometimes symbols are important because
yes,
they communicate
it was
something.
a way to distinguish.
No. A0 is always relevant to the unknown in my language.
Okay.
Okay. So A0, C0. Simply a matter of symbolizing. It is important because symbols are telling something.
Okay.
Okay. In order to calculate C log, from the data of the problem, we must again discuss an ideal case. Okay? Suppose that we have the blank, that is a sample where we are sure that the analyte is absent. It is ideal because we can never prove that the analyte is not present. It can be present in a real sample. The analyte could be present in a very small quantity. But we suppose that we have the blank. Okay, we have the real blank. Let us make an example. We wanted to quantify copper in red wine. You know that copper is used to kill some organisms that are pathologic for wine. So red wine could have traces of copper. What is blank in that case? A needle red wine where neither one atom of copper is present. It is ideal. I can never be sure, but I can discuss about. So I suppose, so ideal discussion, I have the blank. Okay, I take this solution and I measure it a lot of times, infinite times. And I can put, pay attention, on the horizontal axis all the possible value of y for the blank. Okay? So I have measured the signal for the blank infinite times. So I am going to create a distribution. And this distribution will have a point of maximum, that is what I have called YB, and it will have a standard deviation that I will call SB. Okay. The choice of the analytical chemistry is that Y load, so the minimum signal that I decide is enough higher than YB is YB plus 3 times SB. So I decide this. If my signal is far from YB, at least 3 times the standard deviation, it is significant. Okay? Is it clear for you? So I take SB, I write 3 times, and I obtain Y log. Okay, the picture is not so so correct because I should go write 3 times SB. But here I have the signal of the blank, and suppose that here I put, I want to write it in red. And here is the minimum signal that I decide it is enough higher than YB. Okay?
Yes.
Are you able to tell me how much area is here?
0.3%.
Exactly.
No, well, 0.15 here.
3 sigma. We move from the maximum 3, the standard
No, yes,
deviations.
but just this part is half
Yes,
of 0.3.
yes, because it is 2 tails. Okay.
And
So I want that this tail is very, very low, 0.5 or 0.3%, because I want that the risk of saying that the analyte is present is the risk of being wrong in saying that the analyte is present should be low risk. I mean, in this situation, if I observe this signal, Y0, okay, if I observe that value of signal for my unknown, I decide the analyte is present because Y0 is higher than Y lot. Is it clear for you? I am comparing signal.
can we repeat this?
Okay, if in green I write down the signal that I measured for my unknown sample,
Yes, sir.
I decide that in that unknown sample the analyte is present because its signal is higher than the signal of the limit of detection.
No. Because outside the Y load, sorry, I have something that I can detect,
Yeah.
right?
Why not has this meaning? Because the definition is here. The mean signal that is significantly different from the signal of the blank.
Yes.
Means that every signal higher than Y log will tell to us that there is something more than the blank, there is the analyte. This is the meaning of the YLOD. So, if my unknown has a signal higher than the limit of detection, I state that the analyte is significantly present. There is the analyte. Okay?
No. I can understand the connection. Why we choose low risk to assess that E-load is significantly different from.
I did not explain that. We want a low risk to say that the analyte is present while it was not true. So we want a low risk to be wrong in saying the analyte is present? The discussion is, I know, it is a little complicated, but try to follow me.
Exactly. Can we recap?
Okay.
Well, I understood that I log is sufficiently far from IB to be defined as the
Minimum significant
signal. Exactly.
Yes.
Now we know that these details are 0.3 probability, and it represents a low risk because we want a low risk in saying that the
analyte is present while it was absent. We want a low risk to be wrong in assessing that the analyte is present.
But that when we measure the blank, not when we insert an unknown sample.
Let's try to change strategies. Okay. Now look at the picture and follow with your eyes the black curve.
Yes.
The black curve are points that are saying in these points the analyte is absent. Okay? So
yes,
all the points of the black curve are saying in us the analyte is absent.
Yes.
So to say that an analyte is present, I should go to infinity. So I can't say that I need an infinite signal. So I make this choice. I look at the point where we live in the tail, the red tail, only a very little area. That red area is the risk of being wrong in saying the analyte is present. It is a concept you could try to.
No, I understood, but why? In order to understand the blank, because I mean I0 is our analyte.
Is the signal of our analyte, yes.
But if we are in the blank, we don't have.
Yes, but the blank is ideal. I mean, it is a needle reasoning, it is a needle discussion. Okay, let us change another strategy. Still another strategy. You have the signal of the blank, okay? This number. And you want to decide when the green signal, Y0, is high enough. This is what you want, okay? To decide when Y0 is high enough. In theory, you should go to infinity, but you cannot. You must choose a finite number. So you choose a number that lives in the tails few points. Because the tails, the red tail, is an estimation of the risk of being wrong in saying that the analyte is present. I think that if we cannot understand this concept, we must take it as a definition. Because the tails, do you agree that the tails are the risk of errors? Because we said that significance is the risk of being
wrong. Yes,
the risk to be wrong in saying that something is comparable to our interval. Okay, rely on me because otherwise we cannot finish the lesson.
So the tails represent the risk to be wrong in saying what?
The red tail is the risk of being wrong in saying that an analyte is present. Okay. So rely on me is true. And now we want, this is an legal discussion, and nobody of us can calculate or measure YB and SB because we do not have the blank. But we can estimate these two parameters because, okay, let us write again the relationship, this one. The minimum signal for us has to be calculated as the signal of the blank plus 3 times the standard deviation of the blank. But we have also, this is the equation 1, we have also obtained the relationship between y and x because we know that the model holds true. Y is equal to a, the intercept, plus the slope of the model multiplied x. Is it okay? Okay. Now, the blank is when concentration x is 0. When the concentration x is 0, how much is y? It is equal to the intercept. So the best estimation of YB is the intercept of the model of calibration. Is it okay? Okay. Now, we can demonstrate that the best estimation of the standard deviation of the blank is the standard deviation of regression. This means that from equation 2, we obtain equation 3, that is from equation 1, we obtain that YLOD is approximately equal to the intercept plus 3 times the standard deviation of regression. Okay? Do you agree that also this equation holds true, equation 4? It comes from, this is true, it comes from equation 2. Equation 2 implies equation 4, where YLOD is equal to intercept plus slope multiplied x0. Is it true?
Yes.
Oh, it is not true. Can you deduce what should I write here? To y naught is corresponding to the minimum signal. It does correspond to the minimum concentration. I wrote wrong before. It is XLOD. Because we have written here YLOD is the minimum signal, and it corresponds to CLOD. Of course, C and X, maybe this is confusing if you want. Here, I write X. X is concentration. Okay? So, the minimum signal detectable YLOD corresponds to the minimum concentration XLOD. Is it better now? So I can take equation 3 and equation 4 and compare them because they are computing the same quantity, YLOD. So the numbers on the right can be put equal to each other. So I will rewrite it in another slide. So equation 3 and equation 4. Yeah. Equation 3 was y naught equal to intercept plus 3 times sy over x. Equation 4 is YLE equal to intercept plus slope multiplied XLOD. So these quantities are equal. This one and this one. Okay? And by putting them equal, I obtain the conclusion. So A plus 3 times sy over x equal to A plus slope multiplied XLOD. So the minimum concentration XLOD can be estimated by taking 3 times sy over x and divided by the slope. Okay, the only doubt that remains is why that red tail is that risk. Okay, so try to, maybe you can try to read something. You are Italian, yeah, I have Italian notes uploaded. For the not Italian students, I can give to you also the book, the PDF of the book, where these concepts are described, if you want, in English. But it is easier with the translators to translate Italian in English as you want. So you can find in these notes the explanation of why that red tail is an error. It is the risk to be wrong in saying that the amaranth is present. Okay? That's the only, I think it is the only doubt remaining. Okay, we have 10 minutes. I don't know if you wanted to start with the exercise or you are too tired. If you are too tired,
I think before doing the exercise, I need to.
Okay, try to read again,
Yes.
and I can try to give to you some more explanations in Italian. It is easier for me because the statistics is done like that. The tails are risks.
But
risks.
I know absolutely what the days are, what the significance level is. I understood everything. The problem is that I cannot get. Well, I can think the contrary. I mean, the part inside, so the probability, is the probability to don't have the analyte inside.
Exactly. We can discuss like that. Maybe it leads us to the comprehension. So when I find that the green number, y0, is lower than YLOD, I conclude the analyte is not significantly present. It is under the limit of detection. But if the signal falls in the tail, I say the quantity of analyte in my sample is significant. It is significantly higher than the minimum signal.
Mm-hmm.
But the red area represents the error to be wrong, the risk to be wrong, because the black curve is saying the analyte is absent, but the green value is higher than the minimum detectable.
Yes, but
so
why?
This is a risk.
But why we want a low risk in saying that it is
this
present?
is a good question, because the risk of being wrong in saying that it is present is worse than saying I can say nothing. That is, when you are saying the analyte is present, you are saying a strong sentence.
Okay.
And if you are...
Okay. Okay, absolutely clear.
Okay.
Of course, because we want to be sure that the analyte is present.
Yes.
Okay.
Yes. That's
fantastic.
Is there any other? We have just 5 minutes to try to solve any doubt, or make comments. I know that statistics is boring because frequently it uses ideal way of discussing and compares ideality with the reality. But this is the way of discussing that this discipline has. So we state that what is in the tails of distribution is the risk of being wrong in saying that we are outside the distribution. Okay, I think it is better. But anyway, I think that maybe you have understood what is the importance of the limit of detection, because I know that after calculating the limit of detection, I know that analytical method, is not suitable for lower concentrations. So if I find that with LC the minimum concentration is 1 ppm, I know that I cannot use liquid chromatography for samples whose concentration is around ppb, because the limit of detection is too high. There are techniques that go in the order of ppb. some kind of spectrophotometry. I don't know whether you studied the inductively coupled plasma. That is a technique where you nebulize your sample in a source where the temperature is enormous, so the sample is atomized and the signal is very high, so you can see PPB. There are some techniques. I think that in this master you cannot study all the analytical chemistry techniques, but there are techniques suitable for exploring concentration very low in the PPB, part per billion or part per trillion. We can go down, but with other techniques, not liquid chromatography. Okay, so we will change our program like that. Tomorrow in the morning, I will show you how to make the exercise for calculating the model, the calibration model in the external standard method. And after, in the morning, you will try to make an exercise by yourself. And in the afternoon, I will describe the standard addition method and the criteria for choosing when I can apply the external standard method and when I must apply the standard addition method. It is always a matter of stating whether the matrix influences the signal of the analyte. If this influence matrix effect is high, we have to use the standard addition method, otherwise we can use the external standard method. So tomorrow in the afternoon, the standard addition method, and in the last lesson, June the 6th, the propagation of error and some recap of the course and of all the topics that we have faced. Okay, this is the program.